As a software engineer, we have a lot of languages to choose from. Each language is different, and guess what? Type checking happens to be a significant factor into determining which language you want to choose. For what purpose? For example, type checking can be really strict. And in that case, you want that kind of level of strictness because you need high availability of a long-running process. Well, sometimes you don't want that. You want a nice, easy-to-use script that can be very easy to manipulate without having to get impeded by a compiler that sort of holds you back. So, for example, scripting with a Python or a Bash or JavaScript, these are examples of non-strict type checking engines and languages that allow you to be more nimble with how you're programming. And languages like Rust and C and Java require additional compiler restrictions, which hold you back from making mistakes because you're going to need to have an application that's really stable in that case. Well, that's usually what those languages are more used for, right? Because those use cases, like you have an app on your phone or you've got a server that needs to run a long-running process and it needs to be reliable. You want strict type checking for those scenarios. You might find yourself in a situation where you need to build a resilient service that's running or an app that needs to make sure it's not crashing. Those are pretty important reasons to choose the right language. The right compiler for the job is going to be one that has static type checking. With static type checking, we're going to have the ability to check the code before it even runs. That's the whole point of the idea behind static type checking. That word static means the code's not actually running, it's not executing. The compiler will look over the code and make some checks. It's going to validate a lot of things. And with static type checking, it's going to make sure that you don't do any accidents, right? For example, you've got C, C++, Java, Rust, and Haskell. Those are languages at compile time, so before you can even run the code, they're going to look over your code, read the code, and make sure that you didn't assign a variable to a different kind of data type, right? So you can have an integer and then you can have a string, right? A series of characters. That data type you cannot change, and if you do it, the compiler will stop you, which helps protect against some of the common problems that we run into. For example, detecting type errors early on in the development process will lead to more optimized code. It'll be faster because the compiler knows how to deal with it, and it knows that it never has to deal with changing data types. And then also safer code, right? We need the code to be able to run continuously without interruption for users. Then we scroll down over here to disadvantages, and it can be less flexible, static type checking, right? We want to make sure that when we're using static type checking, we know that it's not going to be as flexible from the scenario where we need to write a quick script, right? If we need to write something that's really quick, that's going to do a one-time thing, or it runs, in a batch scenario, we don't necessarily need to use something as strict as static type checking. Dynamic type checking sounds really cool, right? It sounds like, ooh, that sounds fancy. I have the ability to run my code and it will be dynamic. So it sounds like it's like streamlined and seamless. It turns out this is actually pretty good in some cases. Like, for example, I'm writing a script that needs to be flexible, Python, Ruby, JavaScript, and PHP. In these cases, these are programs that determine the meaning of data types and variables the time the program executes. So as the code's running is when the type is understood. For example, this could be a problem when you write some code that tries to do an action assuming that it's a different kind of data type, like you're trying to add a number into a, for example, let's say, I don't know, a string, right? Like what's the behavior that's supposed to happen there? You might have a string concatenation that occurs automatically through coercion. Some of these languages will do that for you, which is a nice reason to have dynamic type checking because it makes a language a little easier for the human to read. You kind of know what's going on. You might know that it's a good thing. You might intend it, though under those scenarios, you'll have problems. So let's take a look at some of the advantages. For example, the flexible and easy to write, right? It's also easy to read, and you can have polymorphism and duck typing. If it doesn't matter if it is a duck, it just matters if it quacks. I like that. The disadvantages are errors can only really be detected during the program's execution. So this is a problem because that means that you can write code that there's no compiler that's going to do extra checking before you deploy your code. You need to run your code in order to see if there's any errors. The problem is specifically with relying on that, you need to exercise all of your code paths which means more work. If you need a reliable and stable system, you'll need to write a whole bunch of unit tests and integration tests that cover the full code end to end. Now, for example, that is going to provide you more work. If you're trying to build a service that needs to be up and running continuously and reliable and fast and performant, you're going to be trading that off for that flexibility. I really like this. This helps improve the readability of the code. Type inferencing is a capability of a compiler to determine what kind of data type a variable is at the moment of assignment, which is kind of great because that means it reduces the overall burden of the code that the human has to write, or I guess the AI in this case. It means there's less code. And so instead of declaring what data type is going to be, for example, an integer, you can just name the variable and then assign it to the data type, for example, a number. The compiler knows what you mean there, and you do not need to annotate that data variable assignment or the definition of the variable, which is great because that means there's less code. The compiler can still help out. This is a capability that a lot of languages have built-in inherent. Even the strict compiled languages and static typing languages, they allow you to do these kinds of things because it's automatically determined based on how it's being used. So there are a couple of examples of Haskell and Kotlin here, TypeScript 2. The balance of flexibility and dynamic typing with the safety of static typing, right? So you can still get a little bit of dynamic typing, not a whole lot. It's not really dynamic typing. I mean, it's really saying you can define a variable and then later assign it to a data type. Now, with static typing, of course, you want to static type checking. You will not be wanting to change that data type unless you specifically set up a conversion function, right? So you want to convert a number into a string. You have to specifically program how that works, and that is possible. Obviously, the disadvantage is it can be complex for the compiler to implement, so you need an advanced compiler. And then sometimes the infer types may not be what you actually intended, so there could be some side effects here. With data types in programming languages, we have strong typing and weak typing. They're both different. With strong typing in a programming language, you're going to have some explicit requirements for type conversion. For example, you cannot implicitly convert a data type just by throwing an operator in front of it, for example, like Java, C#, Ada, and Pascal. These languages prevent you from implicitly converting a data type. You can explicitly convert data types. You have to use methods like a .toString, so you can convert a number into a string. Those are allowed. Any other kinds of type conversions are prevented. Now, a weak typing language, for example, is like JavaScript, where you can have coercion occur where you have a string and you can convert it into a number simply by throwing a unary operator in front of it, though often that can lead to situations that you don't want. You'll get outputs such as not a number or undefined, which is problematic. However, usually it's fine because what you're trying to do in some of the cases is just create a quick script that takes care of what you exactly need it to do just for that one moment. I also like this concept of duck typing in programming languages that involves objects, methods, and properties being used to determine that it's a suitability for a particular role, and it can be whatever you want, which means you can have an object of any kind or type, and then as long as it has the methods available to it, then it's completely fine that you treat it as whatever you're trying to treat it as. The quote is, I really like it, if it looks like a duck, swims like a duck, and it quacks like a duck, then it's probably a duck. These are all methods that are built into the object itself. It can appear as a duck, and it has the swim capability, and it has the quack capability. Then it's probably a duck, but it could be something else. It could be anything. It looks like this. It's actually really straightforward. You have a duck, and then you have a person, and then you have a quack method. So we have duck, quack. So it's probably a duck. Actually, in this case, we know it's a duck because it is a duck. You can also have a person that quacks. Guess what? They both do the same thing, and you can make the thing quack. And so guess what? That is the idea of duck typing.